this video, I'll be telling you how to search, delete, and insert into a binary search tree. But first, I'm going to tell you why you would want to use a binary search tree in the first place. And the one big thing is about search times inside your data. In a binary search tree, a perfect binary search tree where it's not unbalanced is a balanced binary search tree, meaning every node in the tree has two children, and not one side of it is has more nodes than the other side of it. If it's like that, a balanced binary search tree, it has a big O, search big O, log n. Meaning that it takes log n seconds, n meaning the amount of nodes in the tree, to search through that entire tree. While in a regular linked list, which trees are based off of, it's O n. O n, meaning it takes n amount of times. That would be if it's completely random. And then a tree can actually get there to a big O of n if it's unbalanced, meaning all of the entries are pretty much in a linked list, meaning that all of them are either in the left child or all of them are in the left or the right child, depending on how unbalanced it is. So in a perfect binary search tree, the fastest it can go is log n, and the slowest it'll go is n. First, before we start in inserting nodes into a tree, I'm going to tell you a couple things. So in a tree, I'm not going to put anything in there yet, but it looks like this when you write them out. So this is a very basic tree with the root of the tree being the top, and then a leaf being the very end. This is the parent node. This is the child node. Child node. So in a binary search tree, a parent can only have at most two children, and every child has at most one parent. That's how it goes. And in a binary search tree, if we were to put numbers to them, the left child is always smaller than the parent. So let's say the parent is 20. If I were to look at any of the leftmost children, it will always be smaller than 20. So 1 through 19 would be in the left, and 21 and above will be in the right side. So this can be 1 through 19, and then this will be 21 to infinity. We wouldn't want this to be the case for the root node of 20 in a binary search tree, because then that would push you to be a big O of n, which would be an unbalanced tree. But if you have only a few nodes entered, it's fine. Yeah, so smallest one goes left, bigger one goes right. So if we were to insert nodes in a tree, first we need some kind of data to insert in the tree. So let's say, let's go 15, 22, 8, 3, 17, 25, 1. Let's go with more. 33, 16. That seems good enough. So these will be all of our nodes that we'll be putting into the tree. The first one, so one of the ones you start off at, is the root node. So let's create our root node, being 15. So 15 is the root. That's where you start. It's like in a linked list, how you have a head, that's where you start. It's the same thing, but it's called a root. And that will have eventually two kids. Right now it has no kids, so it points to a null left node and a null right node. So it's just one node with nothing else. And then what we'll do next is insert 22. And like I said before, let's say the right child nodes will always be bigger than the root. And the left child nodes will always be smaller than the root. So in this case, when we insert 22, 22 is bigger than 15, so 22 will be over here. And then you go through it again, you go through 8. 8 is smaller than 15, so 15, 8 is smaller than 50, so 8 will be over here on the left side, because it's smaller. And then these two both would have null pointers going left and right. 8. And then you go and insert 3, you say, okay, 3, I have 3 is less than 15, go left. Is 3 less than 8? Yes, go left. 3. And then you go to 17. So 17 is bigger than 15. You go to the next child, which is right. It's right child. It's 22. 22 is bigger than 17. So then that means 17 is smaller than the parent. So you go left. Smaller than that. 17. Then choose null pointers, left and right. You look at 25. 25 is bigger, so you go to the right. 25 is bigger than 22, so you go to the right again. 25. Then insert 1. 1 is smaller than 15, so you go left. 1 is smaller than 8, so you go right. 1 is smaller than 3, so you go left. 33, you go 15, it's bigger than 15. 33 is bigger than 15, so you go right. 33 is bigger than 22, so you go right. And 33 is bigger than 25, so you go right once more. 23. And then you got 16. So 16 is bigger than 15, so you go to the right. Smaller than 22, so you go to the left. Smaller than 17, so you go to the left. Okay. Now we have, and then these are the null pointers. And now that we're at the end, we've inserted all of our nodes. So this is what our tree will look like. The smallest one's always on the left, and the biggest one all the way to the right. Now, if we were to search in this tree, it's the same thing as you would if you were to be inserting, except for in this case, we're just trying to compare the node to whatever we're trying to find. So let's say we're trying to find 17. Search 17. So you look at the root node, which is where you always start. You start for inserting, deleting, and searching, always at the root node, which is the top. And you say, okay, compare 15 and 17. So 17 is bigger than 15, so you go to the right. And you look at 22 is the next one. 17 is smaller than 22. Since it's smaller, you go to the left. And then you found 17 is your node. So 17 exists. You would take whatever you want. Like, let's say some other data you have. Let's say 17 equates to a name, and 17 is John. Let's say all these also equate to names. So that's why you're putting them in there. Let's say we want to find something that we don't have. Let's say 100. So you look at 100. You search for 100. Bigger than 15. Go to the right. Is it bigger than 22? Yep. 100 is bigger than 22. Go to the right. It's bigger than 25. Go to the right. Bigger than 33. Go to the right. Oh, you hit a null pointer. That's at the end. That means 100 does not exist in this tree. And the same thing if you do 24. So you go 15 is smaller. So you go to the right. 24 is bigger than 22, go to the right. 25 is bigger, so you go to the left. But nothing exists there. Forgot to draw this. Nothing exists there, so you have a null pointer at 20, where 24 would be if it existed. But it does not, so null pointer, hence the lack of nodes. Then you wouldn't find it, so you would return that 24 does not exist. Same thing with 100. Once you got all the way down, 100 does exist. And so that's the point of a binary search tree. It's very helpful. You don't have to look at every single node. Once you go to the right, you cut off pretty much half of them. 3 of them you don't even have to look at. You just know it's bigger. If you go this way, let's say 100 is bigger, you don't even have to look at these. And then you go, don't have to look at these 2, and you just have some more to look at. Hence, if you do anything less than 15, you don't have 5 to look at. You just have 3 other ones, so 4 in total. If you do anything smaller than 15 and bigger than 15, you have to look at these 3. But that's one small downside if you have a smaller root node, is that they could have less things on the left and more on the right, or vice versa. If it's a bigger root node, you have more nodes over here, and so then it defeats the purpose of having log n as a perfect binary search tree. It's pretty good here. You cut off 3, and then you have to look at a couple, especially if you go over this way. It's pretty good. And that's it. And then we'll move on to how to delete. So if we were to delete a node in this, we'll start off by deleting the root node. There are 3 types of deletes you can do. You can do the root node, a leaf, or any of the internal nodes. Every node, I just would like to point out, every node should be either a child or a parent. The only ones that aren't parents are bottom leaf nodes, because they are all children. So whenever you go, if you look at one, you can delete it. Let's say I'll move ahead to something. Let's say we delete 22. 22 is the parent of 17, 25, and it's also the child of 15, just so you point out. So if we were to delete 22, first you cross it out, so you X it out, and then since the 2 things you need to do is you either look at the left children, and you get the biggest of the left children, or you go to the right, and you find the smallest of the rightmost children. So let's go biggest of the left, that's easy. So we just pull 17 up. So then we replace this with 17, so it just becomes 15 over is 17. And then you still keep the connections between those two. It's 16, because then you keep the binary search tree how it's supposed to be, where the left is smaller, right is bigger. And then you connect it 25, 30, 30. And then this whole side doesn't even get affected, because you didn't even worry about it. You go this way, you go 8, and 3, and 1. And then if we were to delete 15 as the root node, all you do is you cross it out, so you deleted it, and so you have two options. You can go the biggest to the left, or you can do the smallest to the right. So if we were to do the smallest to the right, we would choose 16. If we were to do the biggest to the left, we would choose 8. So let's say we choose 16, that's pretty easy. You just move it up to the now become the root node, you delete this, and then you connect it all the same. So you just replace those two, and you get rid of 16. So let's write that out over underneath. So 16, 17, 25, 30, 3, hopefully you can see that, 8, 3, and 1. Now it's a pretty ugly binary search tree. It's a little ugly, like it's half and half. So it's better than something like that, which would just be essentially a linked list. But it's still pretty good. That's how you do it. That's how you delete nodes, is you look at wherever you are, you check it's both one more option, is if any of the root nodes, any of the leaves or the very endmost children have been deleted, all you do is just delete that one, you don't even have to worry about the rest of them. Because there's no other children below it that's going to be messed up. Be like, I don't know what's connected to you. So then you just keep it how the same. So if we were to delete one, this is what our tree would look like. If we delete 33, that's what our tree would look like. So that's how you, because there's no other children connected to it, so you don't have to worry. Those are the easy ones. But other than that, if you delete any other nodes, other than any nodes with children, you look at the children and you replace that node with either the smallest one on the left, the biggest one on the left, or the smallest one on the right. The way to remember that is it's the opposite of inserting. So if you go to the left, you typically would have a smaller number, but you would want the biggest one on the smallest side, or you do the smallest one on the biggest side, because the right is typically the biggest numbers, so you want the smallest of that one. And the reason you do that is because it keeps that binary search tree, its capabilities, or it's the way it works is that the smallest one's always left and always right. So if we were to go back over here, if we replaced 15, you would want to take 8, bring it up here, so now it'd be 8 connected to 22. So if you go into the right, all of these are bigger than 8, and all of these are smaller than 8, so that's why it would work. Same thing if you took 16, replaced it with 15, and 16, delete that one. All of these are bigger, all of these are smaller. Hence the reason you would take the smallest from the right or the biggest from the left. So you have to keep that binary search tree working. And the biggest, smallest, biggest.